Welcome to the second part of integration by substitution. In today's lesson, we are going to learn how to find the definite integral using the substitution method. Keep in mind that before the substitution method was introduced, we only know how to find antiderivative of a few very basic functions. Some of those functions are, and if you don't mind, I'll list them over here. Like, we know how to find the antiderivative of a power function. We know how to do that, right? We know how to find the antiderivative of exponential function. We know how to do that. Just a few functions are possible to find the antiderivative for. Okay, so those are some of the functions that we know how to find antiderivative for, and the substitution method opens up to allow us to find antiderivative for more functions. Now, the substitution method only works if it involves either a product of two functions. So you're looking at maybe a product of two functions like that, or a quotient of two functions, which could be something like this. All right, now the product or the quotient have to somewhat relate to each other. For example, if it is a product of two functions, then the outside function should be the derivative of the inside function. And if it's a quotient of two functions, then the derivative of the top function should be the derivative of the inside bottom function. Okay, so substitution method only works if it kind of follows in this manner. All right, so when you analyze a problem, even before you try to apply the substitution method, you want to see whether or not it fits into this pattern. So for example, say if we're looking at this problem, for example, then we can complete this problem by the substitution method because it does involve the product of two functions. And also, if you look carefully at the outside function, this is the outside function, then that is really the derivative of the inside. The inside is x cubed plus 1, and its derivative is 3x squared. Now, even though you don't see a 3 in front of the x squared, but you know that you can turn that into a 3 by multiplying it by 3. Okay? Therefore, this problem can be done by substitution method. Now, the only thing that's different from what we've accomplished so far is, in addition to finding the antiderivative, we're working with definite integral, which implies that after finding the antiderivative, you evaluate the lower and the upper bound. And it turns out that when we complete substitution method for definite integrals, which are the ones that has lower and upper bound, it turns out that it's actually easier. So this is what it means, but it's best to learn how to do it through examples. So here's what we're going to do. We know that we want to evaluate this definite integral, and we do know that we have to use the substitution method because the outside is the derivative of the inside. The first thing we do is we're going to let u equal to the inside. So let u equal to x cubed plus 1. Immediately take the derivative of u, that is represented by du, over dx, and then eventually we multiply both sides by dx. So if you don't mind, I'm going to skip that step, and the derivative of the right side is 3x squared times dx. Okay, now this is an important step, so maybe I should put it in a box. that. Okay, so keep in mind that now we're going to perform a substitution, but here's the problem though. We do see there is an x squared dx, but we don't see a 3. So before we make that substitution, we need to get rid of that 3. And to get rid of that 3, all you have to do is multiply or divide both sides by 3. Okay? So we have x squared dx, which is right there. So what I'm going to do next is I'm going to go back and I'm going to perform the substitution. If it's harder for you to see the substitution, I would recommend that you copy down the original problem and then instead of writing x squared before the radical, write it after the radical like this. And hopefully now you should be able to see that we're going to make a substitution, so that will be replaced with 1/3 du. Okay, so plug in 1/3 du for that expression and replace this inside expression with the letter u, because that's what u equals to. So that's square root of u. So let's now finish this problem. Okay, now notice that after we change the variable from x to u, we also need to find our new lower and upper bound. These are the original lower and upper bound for the original problem, but because we have expressed our problem in terms of u, we also need to change those bounds. To change those bounds is actually not hard. To change those bounds, what you do is you first identify what u equals to, and so to find the new bound, you're going to replace the old bound into x and find the new bound. So your new lower bound is plug 0 in for x, so your new lower bound is going to be 1. Okay, 1 is going to be your new lower bound. And the upper bound, this was the old upper bound. The new upper bound is replace 2 in for x, and that equals to 9. So that's your new upper bound. Okay, so we go back here and I'm going to replace 1 in there and 9 in there. So the integral from 1 to 9, turn that into exponential form, and now we apply the power rule. So the antiderivative of u to the 1/2 is u to the 3/2 times 2/3, and then we evaluate this from 1 to 9, which means that we're gonna plug 9 in for u. Plug 9 in for u. Raise that to the 3/2 power. Subtract that 2. Plug 1 in for u. Okay. And that gives us, this is going to give us 2/3. This is really 3 squared, so you get 27 minus just 2/3. So that becomes 54/3. Take away 2/3. So that comes out to be 52/3. And you're done. And that's the area under this graph, 52/3. Okay, good. Let's go ahead and move on to the next problem, but let's go back and see what we just did. Alright, so if you want to find the antiderivative for, if you want to evaluate a definite integral and you're using the substitution method, then in addition to making a substitution for the integrand, you're also changing your lower and your upper bound by evaluating the u function at the lower and the upper bound of the original problem. Okay, so don't forget that. Alright, so here's another one, and this one is similar to like g